So in the last class, we spent a little bit of time talking about the argument that justifies hypothesis testing, but I'd like to review that briefly and then move on to some potential objections to hypothesis testing. So defenders of frequentist inference really ground hypothesis testing in a statistical model. And we saw this last time with this quote from Spanos, this philosopher of statistics, who says that we should model our data generating process using a statistical model that is both optimal in some sense that we'll describe and also adequate. And as a reminder, this statistical model is really a class of probability distributions that model your data, and it's parameterized by a parameter theta. Theta could be a vector of many parameters. And in hypothesis testing, we typically take some values of theta, maybe just one, for our null hypothesis, and then some other set of values, some interval maybe, as an alternative. And then from there, we may have some test statistic. The test statistic is a function of your the random variables that generate your data, and that test statistic is random based on how the data are modeled. So the random process really comes from imagining that you have a data set in front of you. Those data are generated from some random process, meaning if you were to sample from that population again, you would get different values generated by the random variables. So what does it mean for a model to be optimal and adequate? Well, optimal is something quite mathematical, and it has to do with the balancing of error rates. So in a mathematical statistics course, you might study uniformly most powerful tests, and those would be tests that at a specific alpha, which is a type 1 error rate, could you derive a test that is the best in terms of its power, meaning it has the highest power, or equivalently the lowest type 2 error rate. So an optimal test would be one for a given type 1 error, the best possible power. Doesn't always exist, but sometimes it does. An adequate model would mean a model that really does a good job of describing the data generating mechanism and then specifically the data that you have in front of you. So do you have the relationships between variables correct? Are you assuming independence when it's warranted, or are you making independence assumptions that aren't warranted? All of those sorts of things go into the adequacy of a model. Another adequacy consideration is the mapping between a scientific research question or business question and a statistical model. And there could be a mismatch there. It could be that you sort of misencode your research question into a statistical model that doesn't really answer the original question. And that's an example of what some people call a type 3 error. So the specific argument that justifies hypothesis testing starts with an assumption about a null hypothesis. And so I've got a null hypothesis written here. You assume the null, and then often you specify some alternative. So we had this on a previous slide. Maybe that the true theta is greater than some specific value theta naught. And then under the null, you would compute a test statistic. Test statistic is, again, a random quantity based on an argument about resampling. And you can compute the probability that the test statistic is at least as extreme as the one that you actually observed. And that probability, if you compute it under the null hypothesis, is the p-value. And then often hypothesis tests are evaluated based on comparing the p-value with some alpha level that's pre-specified in the test. So if the p-value is small, we might say that we reject the null hypothesis. You might say that you have evidence against the null hypothesis, although some might object to this phrase evidence, using probability to quantify evidence for a p-value. But standard thing to say is that we reject the null. Whether we believe the null is false is a bit tricky because belief is typically associated with probabilities. Probabilities, many people think, describe partial beliefs. And a p-value is not a belief probability. It is not a probability that the null is true, for example. So it doesn't seem appropriate to talk about belief here in terms of a hypothesis test because frequentists don't use probability in that way. Now, the notion of implausible is pretty interesting. So implausible seems to also conjure up the notion of probability. If something is implausible, it might mean that it has a low probability. And so some people think it's not appropriate to claim that a null hypothesis is implausible if you get a small p-value, because that is sort of smuggling in probability in a place where it's inappropriate. So alternatively, you might find a large p-value. And in that case, the most appropriate thing to say is that you fail to reject the null hypothesis. And this has this falsification logic that we've described earlier in this course. Falsification meaning you pose some theory or hypothesis and you try to disprove it or build up evidence against it. And just because in this specific test we didn't find evidence against the null hypothesis, that doesn't mean that the null is more likely to be true or that we should accept the null. So it's probably not right to say for any given hypothesis test that we accept the null. So that's kind of the rough structure of the logic of a hypothesis test. And there's sort of two fallacies that I want to alert you about. The first is the fallacy of acceptance. That's one that we kind of just mentioned. So if you have if you have a large p-value, you could claim there's no evidence against the null hypothesis, but of course that as a fallacy would be misinterpreted as evidence for the null. So the fallacy of acceptance is this misinterpretation of a large p-value as evidence for the null hypothesis. So fallacies we should avoid, right? The fallacy of rejection is a little bit maybe more interesting. So evidence against the null, that would be a large p-value, in this fallacy would be misinterpreted as evidence for some particular alternative hypothesis. Remember, alternative hypotheses are usually contain lots of potential values, right? In this case, infinitely many values of the parameter theta. And so just because you've rejected the null, it doesn't mean that you have evidence for any single value, right, in some interval, right? We've got just an interval that kind of starts at theta naught, right? This is the null hypothesis. And if you've rejected the null, you're somewhere along this interval, but you don't have specific evidence that you're way out here versus much closer. So this is a fallacy if you sort of think that if you have a really small p-value, you must be way out in the alternative. That's often not the case. And Mayo and Spanos, these philosophers of statistics, have developed a concept and a sort of technical way of trying to assess how far out you might be in the alternative or how close you might be to the null. And it's called severity, and we'll study severity in a later lesson.